Okay, we're continuing with derivatives of inverse functions, and now we're doing the derivatives of inverse trig functions. And I'm not going to derive these for you today because I don't think you're ever going to do that in random life if you just forget. So this is the derivative of inverse sine. Inverse sine is the same as arc sine. They're interchangeable. So the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. If you do the derivative of inverse cosine, it is the exact same with a negative. The derivative of inverse secant x is 1 over the absolute value of x times the square root of x squared minus 1. The derivative of inverse cosecant is the same as inverse secant with a negative. The derivative of inverse tangent x is 1 over x squared plus 1, and the derivative of inverse cotangent is the same with a negative sign. Okay, so let's try these. Example 1, find the derivative. Okay, so the derivative, we're finding the derivative of inverse sine. We are going to use the chain rule because in the parentheses we have the 3x. Okay, so inverse sine, derivative of inverse sine is going to look like this. So it is going to be 1 over the square root of 1 minus, and instead of x, I'm going to put the quantity, and I am doing the inverse sine on squared. And then because of the 3x, we're going to go ahead and times by 3 for the chain rule. And I think I'm just going to simplify it a little bit. So 1 times 3, that's 3. And I'm going to make the radical 1 minus 9x squared. We have no objections to radicals in the denominator, so I'm going to leave it like that. Okay, let's try B, the derivative of the inverse tangent of 2x squared. Okay, and again, I'm going to use chain rule because I can see there's an inner function. But let's start with inverse tangent. The derivative of inverse tangent is 1 over x squared plus 1. So 1 over, when they say x squared though, they mean the quantity you are taking the inverse tangent of. And then times the derivative of the inner function, which is the 4x, and I'm just going to clean it up a little. So 1 times 4x is 4x. If I distribute the bottom, that's 4x to the 4th plus 1. Okay, and I would say inverse sine and inverse tangent are the most common of these inverse trig functions you're going to do derivatives of. Okay, the derivative of arc secant 5x. Arc secant is the exact same as inverse secant, and this is going to be chain rule because of the 5x. So this is going to be 1 over the absolute value of whatever's in the parentheses times the square root of the quantity squared minus 1. Chain rule. So if I do since I am doing the arc secant of 5x, I'm going to times it by 5. And I'm just putting it at the top so it is easier. Okay, now I want to simplify this a little bit. So if I look at this, I have 1 times 5. I have a 5 at the top, and then I have an absolute value of 5x at the bottom. Can I cancel the 5s? I can cancel the 5s because if I do the absolute value of 5, I'm also going to get 5. So I am going to cancel this 5 with this 5. Because they're both positive, they're going to cancel out. Do I need the absolute value on the x? I do need the absolute value on the x because this needs to be a positive quantity. And if I lose the absolute value, it might be negative. I'm going to go ahead and distribute 5x squared to 25x squared minus 1. And then I'm going to leave this as my simplified answer. Okay, one more derivative of inverse secant to show us the canceling situation. Okay, and we're doing chain rule again. Okay, so the derivative of inverse secant is 1 over the absolute value of 2x squared times the quantity squared minus 1, and then chain rule, I'm going to times 4x. Okay, let's see what we can cancel here. Okay, I can for sure cancel the 4 with the 2, and that's going to take it down to a 2. Actually, I'm going to take it one more step, and then I'm going to cancel it. So 1 times 4x is 4x. Now the question, do I need the absolute value on the 2x squared? The absolute value is 2, so I definitely don't need it there. Do I need the absolute value on the x squared? I do not, because x squared is going to turn it positive. So it's not necessary to put the absolute value on it. And then I'm going to make this 4x to the fourth minus 1. Okay, now that it looks like that, I can simplify the 4 and the 2. Okay, can I cancel an x out? I can now. Okay, and then this is my simplified answer. I didn't need the absolute value, and I was able to cancel out an x. And it's because when I was absolute valuing the x squared, the absolute value was redundant. So I could cancel it out or get rid of the absolute value. The other reason is if x is negative here, this would be negative, this would be positive, so this result would be negative. If I look at the final answer, if the x is negative, I'm still going to get a negative result. It's not going to mess up my signs, is what I'm saying. Okay, this is not calculus. This is just to review your inverse trig, domain, and range. So for inverse sine, this is the exact same thing as arc sine of x. Okay, since the range of sine is -1 to 1, the domain of arcsine is from -1 to 1. The input to arcsine is between -1 and 1, and then the range is normally the radian value at which that sine value occurs. Okay, because this is a function and we don't repeat values, we limit this to 2 quadrants. For arcsine, the sine is -1 at the bottom, it is +1 at the top. So the range of arcsine is from -π/2 to π/2. So if I do arcsine, my answer will always be between -π/2 and π/2, or it will be one of those answers. So if I do the arcsine of 1, I think about where's the sine equal to 1? Sine is equal to 1 up here, which is in the correct range. So from here to here, if I go in the positive direction, the answer is π/2. If I want to do the inverse sine of -√2/2, I want to see where the sine is -√2/2, but I have to stay within these 2 quadrants because technically it's in 2 spaces. This is the only one that matters. So I want this location here. Because I'm going from -π/2 to π/2, if I start here, I have to call this -π/4. Okay, it won't be called 7π/4 because that's not within the domain. So I start from here, and if I go down, I'm going in the negative direction. If I go up, I'm going in the positive direction. Okay, let's think about inverse cosine x. This is the exact same as arc cosine x. Because the range of cosine is -1 to 1, the domain of arc cosine is -1 to 1. Okay, arc cosine has a limited range in order to make it a function. So if I look at the unit circle, I think about where's the cosine -1? It's -1 on the left. It's +1 on the right. So we use quadrants 1 and 2. We always use quadrant 1, so from 1 to 2. This is from 0 to pi. So when I do arc cosine, my output should always be between 0 and pi. So if I do the arc cosine of -1/2, I'm looking for the x coordinate to be -1/2, which happens here and here. But because of the restrictions, I have to pick this answer here. So the arc cosine of -1/2 is 2π/3, which is between 0 and pi, including 0 and pi. Okay, inverse cosine is 1. Where is that? Well, that's right here. So that's 0. 0 is between 0 and pi, including 0 and pi. Okay, last inverse function we're going to review is inverse tangent, which is the same as arc tangent. Okay, the range of tangent is -∞ to infinity, so the domain of arc tangent is -∞ to infinity. You could do any input you want. Okay, we do restrict it to make it a function. Okay, we go from -∞, which is undefined, which is at the bottom, to +∞, which is at the top. It's -1 divided by 0 to 1 divided by 0. So it's very similar to arcsine. We do parentheses at -π/2 and pi/2 because it's undefined at those 2 values. Okay, so if I do arctangent, my answers have to be in quadrant 1 or 4. In quadrant 1, it's positive. In quadrant 4, it's negative. So tangent is y over x. So where is the y over x equal to -1? That's at the √2/2. So it could be here, or it could be up here in this quadrant. But because this is arctangent, I have to do quadrant 1 of 4. So it has to be quadrant 4. It's at the π/4, but it's going down to π/4. So this is going to be -π/4. Okay, one more. The inverse tangent of 1 over √3. And we don't rationalize it because it makes it harder. Okay, remember this is y over x. So I'm looking for when the y value has some kind of 1 and the x has some kind of √3, which means that y is 1/2 and x is √3/2, which is going to happen right here in quadrant 1, which is at π/6, which is between -π/2 and π/2, which makes it a valid answer for the restrictions of arctangent x.